order of philosophy, mathematics, mathematics education, and cognitive sciences. I think it may shed a little bit more light if I just give a brief background to my activities. I was educated as a professional mathematician in the former Soviet Union, and I graduated from Kharkov State University. And at that time, that was the third mathematical center by any rank in the Soviet Union, after Moscow State University and St. Petersburg at that time, then Leningrad State University. After that, I moved to mathematics education research and physically moved to Australia a while ago. In Australia, I was involved in a number of different mathematical activities and continued working with gifted students. I'm a member of the Australian Mathematical Olympiad Committee, and that gives me actually a broad view on. I work with actually all the children starting from primary school and up to tertiary level. And in particular, my last, my recent activities, it was an attempt. I believe it's successful, but it still needs a little bit of time to understand it better. My attempt to introduce logic and reasoning course for the primary school students in Australia, that's locally, just to help students understand mathematics, overall mathematics, not just the separate activities like counting, problem solving, but overall together mathematics, what mathematics actually represents and how mathematics can be understood. So it's my current research is based and was influenced by my Kosovo paper. Actually, that's not the only one. I will provide all reference full paper, but that was the first that came to my attention. And as my brother said, that there are good reasons to keep separate what might be explanatory in the classroom and what's explanatory for the community of mathematicians. And since I have expertise actually in both areas, it was very interesting for me to start actually doing something that relates to the activities in the classroom and the role of explanation and in the classroom and how we can compare that. That brought me to the broader view how we can understand and actually how we can relate the notions of beauty and understanding in relation to mathematical explanation. And in particular, I came to the conclusion that yes, the notion of beauty is good, but it's worthwhile to consider a broader perspective. And I agree with Alan that that's why I moved from the notion of beauty to the notion of appreciation of mathematics. I agree with Alan that it's something like how much we feel about that and something sentimental. Also, my research, again, I just briefly mentioned several sources here, is based a lot on Gila's work, and I have to admit that working with Gila on the project of Proof and Proving made a huge influence on me. Thank you very much, Gila, for that. And I believe that I became a little bit another person after actually that long work collaboration. So that's again just for several sources I use as a start starting point in my research. And since it still from on the board of philosophy, mathematics, and mathematics education, but I believe that mostly from the side of mathematical education, that's like one-sided limit we consider, where I admit I have much more expertise in. I see that dual interrelation within two models as in the following way, that actually mathematicians can be seen as learners in different situations. And the one example I'd like to discuss briefly here, that's from the same book that was another paper was cited here, Two Cultures by Tim Gores, Mathematics into 21st century, and that's an entire paper there. And he mentioned that when he moved from one research area to another, and there were several such things in his life, before doing any significant research, what he did, he stayed very silent in terms of publication for several years or something like that, and did a lot of research, did a lot of reading, what's going on in that area, what's going on around, and just after that, when he believed that he had enough expertise, he had enough understanding, he decided that he could move ahead and do something on his own. And on the other hand, learners can act as researchers. That's actually very quite recently that became a very popular stream and trend in mathematics education, when teachers been considered as researchers, and that actually had a great response, I believe, from teachers over the world. With the second dual interpretation, learners as researchers, of course, according to their level of mathematical knowledge, what they can do, they can behave themselves, and I observed a lot of such situations. I've noted some records about that, that actually students behave themselves in completely different and interesting way. Here are two examples I'd like to show you and characterize them briefly. What we did, what I did with students. The first one, that's a question from year 4 lesson that I discussed with students, and that's again about different strategies and what actually we can learn from students' way doing such problems.
Oleksiy, I think, sorry to interrupt, but I think the PC is, if you see the icon at the bottom, on the right, on the right, I think it may be threatening to restart itself again. Because we
watch
4 hours have gone. 4 hours ago last.
Just 4 hours. No minutes.
For another
4 hours.
4 hours.
Why I'd like to talk about the first, I have plenty friends now, about the first problem that's actually very short detail. What I observed in the classroom, what students did in terms of strategy. They say, okay, that's 23 children all together. If we try 11 and 12, yes, it doesn't work. But it's somewhere near. So if we just move one kid from here to there, that everything is again, we have 10 girls and 13 boys. The next question was, okay, that's nothing difficult with that problem, but if we have instead that situation, if we have something like that, the total number of students and 197 boys more than girls. How can you sort it out? And after that, actually students start with it. That actually tells us that the strategies they use here, that's, and their explanation based on that strategy, that just guess and check. I admit that unfortunately in many Australian schools that's a problem now, that the main strategy and quite often explanations based on what students do, that's guess and check, which is not good. However, we can use another strategy here, that's what we're trying to do, and actually base our mathematical explanations on that. That if we see that the difference is in 3, we just take away 3, and after that we see that the total number of students should be exactly the same, I mean that, boys and girls. And that's completely different strategy, and what we do, we can stimulate mathematical explanations based on the correct strategy and based on the correct understanding how they can achieve the goal of this problem. So if we just take that number that's different, we have equal 1 at the end of that. The second problem I'd like just to characterize very briefly. That's about a completely different level, and again I use a different level just to show different actually environments, how we can see mathematical explanations work or don't work. This is a problem from the International Mathematical Olympiad of 1998 that took place in Australia, and actually the problem was discussed in many classrooms after that. And the main idea and the mathematical explanations based on that idea in this problem, that's how we can transfer our knowledge. Actually, that knowledge is about solving quadratic equation into the new area, into number theory, and how we can apply that knowledge of solving quadratic equations, just standard technique, and into the new environment where we can use just standard technique. Now, that's a little bit simplified slide. I thought it was to organize the slide, one special slide using LaTeX, but unfortunately didn't have time for that. If we consider two different representations here, on the left, say we have just a brief excerpt from any text, any textbook, say, not matter school text, or say, tertiary textbook on the tertiary level on the calculus. And after that, if we just remove all written description there, and just leave symbolical text, and does it mean that actually all mathematical explanation gone from there? I believe no. I believe no, because what we have there, that's just supporting description. Why I pay attention to that, I noticed that many students, when they listen to lectures in particular at the tertiary level at the universities, what they do, they just make some nodes, symbolical nodes, and no any wording. After that, any supporting wording. After that, they struggle a lot actually to understand what's going on there. But so that's supporting wording is important, but that's still not explanation, proper mathematical explanation. I believe that proper mathematical explanation actually is behind that. And that contributes significantly to students' understanding on their road to understand that material, what they work on, what they study on. Another interesting experiment that I recently did, and actually results were quite unusual and I would say amazing for me. I considered how we can regard explanations versus instructions. And that's a quite common model about introduction of subtraction for negative numbers in primary school, and prospective primary school teachers actually learn that model that's in the textbooks on elementary mathematics. I mean that if we consider 5 minus 3, that's minus turns out to be plus. And that model is about 2 different colors checkers, and we can turn one color checkers to another to get that result. Again, I will provide full reference say for several textbooks that use that model. What I found very interesting that I tried to introduce in the classroom actually straightforward way of instructions. That I didn't try to introduce any model like that. I just mentioned how we can do that. Instead of that, I just introduced that the instruction is the following. If we have minus, that should be plus. And after that, I observed how many students would be not happy with that, saying that why is it so in terms of should it be supported by any explanation on or they just need to follow that. And what I noticed that not in the sense that maybe Mancoso, no, I think it's Hirsch said that convincing proofs that they are not important in the classroom, because actually it's not difficult to convince students in anything. But what I noticed that students were actually happy to follow that instruction. That wasn't something that they were convinced in and did it because they were told to do so. But they were happy to follow instructions, and they got it as just new definition, something like that, and they didn't ask themselves why is it so. Now I'm approaching the second actually part of my presentation, that's about appreciation and beauty and understanding, and in particular beauty as well in mathematics. I already mentioned that when I started this research that the central topic, and actually it still remains the central topic, that's mathematical explanation. But at the same time, I came to the conclusion how it can be related to mathematical explanation, what actual relationships between mathematical explanation and appreciation of mathematics. I talk a little bit why I use appreciation of mathematics rather than beauty of mathematics, and understanding mathematics as well. And what I'd like to distinguish here, that's different types of appreciation of mathematics in terms of it's possible that say an individual appreciates just mathematical fact or property, and without actually any attempt to look what's going on behind the skin. I mean that how that mathematical property was obtained, for example, and why that happens. But at the same time, that's clear evidence that some people enjoy some facts, not questioning is it true or not, is that always true. For example, that's more or less theorem. It's about bisectors of the triangle, which form a equilateral triangle. That's what I did in my experimental work. That when I talked with different categories of people, including high school students and even professional mathematics, mathematicians, asking them about how they can recall that experience when they heard about the property for the first time. Many enjoy that actually without looking at what's going on there. Another type of appreciation of mathematics that relates just a particular object, a mathematical object connected to a particular mathematical object. That's if an individual looks at some proof or solution of some mathematical property or some mathematical fact, I call that dynamic appreciation. So that things actually are not stable and look what's going on behind the skin. I'm not sure it still requires further investigation how they relate to each other. I mean that item number 1 and item number 2, and I believe actually that the relationship is not between them is not straightforward, it's not linear. And that's a possibility that actually both items take place in 1 and 2, and it's possible to appreciate proof as well as theorem as well, and general type of appreciation of mathematics. Again, I'll talk about that a little bit later, but that doesn't relate it. It's not connected with some particular mathematical object or property. It's rather something general, and actually it's maybe just again related to something sentimental in terms of how much that individual feels about mathematics overall, or about particular. Now, relationships, another interesting point that I was looking at this relationship between understanding and appreciation of mathematics, and I'd like to mention here two a little bit unusual, I'd like to give here two a little bit unusual examples about actually mathematics as a social activity. Brandon mentioned yesterday about Gelfand's seminar and quite unusual way how it was conducted over the years. I have to say that since I was born in the former Soviet Union and I can confirm that I was educated there, that way wasn't unusual. That way was quite common, and that I can't say that to play jazz in Moscow State University or somewhere. The same situation took place at Kharkov State University where I was educated. That was quite a common thing that I don't think that actually we have any regulations at the time, but that was quite common that our oral examinations for bachelor degree actually started at 8 AM and they could be finished at 10 PM. And that was nothing extraordinary with that. And actually examination took place in quite similar ways, the seminar. That, okay, do that, and could you please solve one problem? That problem will give you just a grade C. If you can solve 2 other problems, that would be grade B. So by 10 PM, you could achieve just HD, solving something really extraordinary. And in relation to mathematics and democracy, I would say that actually what students that the feeling that students had at the time, most people genuinely suggested that that's real democracy, that it takes place from 8 AM to 8 PM and no any break with human rights and something like that. And that was what I'm trying to explain. That was some kind of special kind of appreciation of mathematics. And since that was something very pleasant for people, I believe all people involved in it. Yes, students were tired. I think that actually examiner was tired as well, but since they related that activity as quite pleasant for both actually categories, they regarded that rather as some kind of special democracy. And, in particular, in that time, it wasn't any democracy. So, another, so that's relationships between understanding and appreciation of mathematics. And another very interesting example, maybe someone from the audience heard about that, but I believe that that's quite rare. That even for me that was quite surprising, despite the fact that I was actually educated there. One quite famous number theorist from Soviet Union at that time, Postnikov. He graduated from Moscow State University just after the Second World War. And his student book, his student records contained, I think, around 70 plus actually grades for different courses, despite the standard situation was just 22 or 24 subject at least to get a bachelor degree. And actually many years after that, when he was interviewed and asked by mathematics magazine correspondent, why did you get so many courses? That was like something like competition with other students, that instead of 24 courses, you took 74, 76. His answer was completely amazing. I would never predict, I could never predict something like that. He told, I was hungry. I was hungry because there was not enough food. It was the end of Second World War, and any kind of food in Moscow at that time, that was luxury. They got actually a piece of bread and maybe something else, but not much. And what he explains that I was hungry, and I noticed that when I'm doing mathematics, that I forget everything. And